Here is a video to help with section 17.3. In chapter 17, we've been learning about enthalpy changes, how heat energy is transferred. In the last section, we looked at energy transferred by direct contact. For example, if you drop hot lead into a container containing cold water, the lead will cool off, give its heat to the water temperature will raise, and that can be measured on a thermometer, which allows you to figure out how much heat was given off by the lead. In that same section, we also looked at thermochemical equations, which are chemical equations that have an additional piece of information written on the end, the delta H value. In this section, we're going to look at heat transfer some more. This time, we'll look at heat transfer that takes place during a change in physical state. For example, when a solid melts and turns into a liquid, heat is transferred. Or when a liquid vaporizes, turning into a gas. Again, there's a heat transfer. The other thing we'll look at in this section is the heat transfer that occurs when a substance dissolves. If you take solid solute particles and dissolve it into liquid water, creating a solution, there will be heat transfer that takes place. The first part of this activity is to do some vocabulary, to look up some definitions. So typically I would have you go in the textbook and find the definitions of these words and then write them in the boxes. You can do that using your textbook or make use of this video. The first vocabulary term we need to get a definition for is molar heat of fusion. In this context, the word fusion means melting. We'll see the word fusion again later in the year when we study nuclear chemistry, and it's going to have a different meaning then. So in the box, write down the definition of molar heat of fusion. And here's the definition. The molar heat of fusion for a substance is the amount of heat absorbed to melt 1 mole of that substance. Next, let's find definitions for these next 4 vocabulary words. Again, they are in the textbook, Chapter 17, Lesson 3. And here are those definitions. Solidification means the same thing as freezing. So our second definition is the amount of heat released to freeze 1 mole of a substance. The third one is molar heat of vaporization. Vaporization is changing liquid into gas. This refers to the amount of heat absorbed to vaporize 1 mole of a substance. The fourth term is molar heat of condensation. Condensation is the process of a vapor turning into a liquid. So this is the amount of heat that's released to condense 1 mole of a substance. The last one does not refer to a phase change between solid, liquid, or gas. It refers to the process of dissolving. The word is molar heat of solution. This is the amount of heat absorbed or released when a substance dissolves in water. So this one could be heat absorbed or heat released. It depends on what the solute is. And therefore, the delta H values for heat of solution could be positive numbers in the case of absorbing heat, or could be negative values in the case of releasing heat. Next, let's fill in the right side of the chart where we give the symbol for these different vocabulary words. The symbol for the molar heat of fusion is delta H, and then as a subscript, FUS, which stands for fusion. So when you see this symbol in writing, it's referring to a number, and the number is the molar heat of fusion, the amount of heat that's absorbed to melt 1 mole of a particular substance. Moving downward, we need the symbol for molar heat of solidification, and it looks like this, delta H, and then as a subscript, solid. It's just an abbreviation for the word solidification. Next one down, delta H, and this time it will often be written as VAP, the abbreviation for vaporization. The next one down, you could maybe take a guess at what it is, delta H, and then the abbreviation for the word condensation is typically COND. And the last one, delta H, and now we want an abbreviation for the word solution. It's common to use SOLN. So these symbols represent those vocabulary words in the left column, and they're actually representing number values for different substances. Now the last column. These values have the same quantity as, but have the opposite sign of what? Fusion, remember, is the same thing as melting. That is the opposite process of freezing or solidifying. So the heat involved in fusing something is simply the opposite of the heat involved in solidifying something. So I'm writing down that delta H fusion is the negative of delta H solidification. In the next row, delta H for solidification is the negative of delta H fusion. Fusion, which means melting, is the opposite process of solidifying. So the heat involved is the same amount of heat, but in one case heat is absorbed and in the other case heat is released. So they have opposite signs. One is positive, and the other is a negative number. The next two are inverse processes of each other. So delta H vaporization is the negative of delta H condensation. And in turn, delta H condensation is the negative of delta H vaporization. The last one I've written in not applicable. Delta H solution doesn't have an opposite process. It's not a phase change. Now that we know the meaning of the vocabulary words and we have symbols to represent them, we can solve some problems that use these concepts. I'm going to scroll down. Here's the first question. Calculate how much heat is used to melt 50 grams of ice at a temperature of 0 degrees. And we're given that delta H fusion for this temperature is 6.00 kilojoules per mole. And there's a spot to write out the solution. Step 1. We need to change our quantity of ice, which is given in grams, into moles. Write down that given quantity and multiply by a conversion factor. The substance is ice, which is water, which has the formula H2O. The molar mass of water was 18.0 grams for every 1 mole. We've used that number 18 as the molar mass of water several times this year. Some of you probably don't even need to look up on the chart anymore for that. On a calculator, 50 divided by 18 is 2.78 moles. That is our quantity of ice, measured in moles instead of being measured in grams. Now step 2. We're going to tackle what we're really asked, which is calculate how much heat is used. Write down the given quantity of ice, and then multiply by a conversion factor. Melting, remember, is the same thing as the fusion. So we want to use the delta H fusion value for ice. Here is the number. If you were to look that up in a chart, if you were to go on the internet and you looked up the substance ice, that would be the number that's given to you. Fill that in. 6.00 kilojoules of energy for every 1 mole of ice that melts. Now we can see the calculation setup. It looks like just multiplying together these two values. The result will be 16.7 kilojoules. We have answered the question. It takes 16.7 kilojoules of heat energy to melt 50 grams of ice at a temperature of 0 degrees Celsius. Moving over to the back side, there's some more problems to try. Calculate how much heat is released to freeze 75 grams of water at 0 degrees Celsius. Hint, the heat of fusion for water was given in the previous example. Step 1. We need our quantity of our substance to be in moles, and it gives it to us in grams. So let's make that conversion. Again, the molar mass of water is 18.0 grams for every 1 mole of H2O molecules. Divide these numbers on the calculator, and the result is 4.17 moles. That is our quantity of water that we intend to freeze. Now, step 2. Let's answer the question where it asks us to calculate how much heat. Write down the quantity of water that we're freezing. Multiply, draw the fraction line, and let's fill in our conversion ratio. We're freezing the water. We're solidifying the water. On the other side of your paper, we wrote down a note to ourselves that it was important to realize that the amount of heat needed to freeze water is the same amount of heat needed to melt the water, but it has the opposite sign. So in the previous question, when it told us that delta H fusion was 6.00, now that we need to know delta H solidification, it's still 6.00, but it has the opposite sign. So we're going to write negative 6.00 kilojoules of energy to freeze every 1 mole of water. Multiply these together on the calculator to get the answer. Negative 25 kilojoules. The fact that this amount of heat has a negative in front of it means that this heat is released from the substance. So the liquid water releases this amount of heat energy when it freezes into ice. Next question. We have 325 grams of water at an initial temperature of 45 degrees. It is cooled until it's frozen at 0 degrees. Calculate how much energy is released during the entire process. We have to consider the energy released when it changes temperature, and we have to consider the energy released when it changes state from liquid into solid. So this is going to take a couple steps of work. Step number 1, we have to change grams into moles, just like we did on the last 2 questions, because it doesn't give us the moles to begin with. So write down the given quantity in grams and make the conversion into moles. Our substance is still water, so 18.0 grams for every 1 mole. The result on the calculator is 18.06 moles. That is how much water we're cooling off and then freezing. Now, step 2. Let's answer the question where it asks us how much energy is released. But there's 2 parts to this process. The first thing going on is there's a temperature change. When the water cools from 45 degrees Celsius down to 0 degrees Celsius, heat energy is going to be lost. The second thing going on is that there is a phase change called freezing. When the liquid water changes into frozen water, energy is released. So let's tackle both of these stages of the process, and then at the end we can combine together the amounts of energy to get that total energy change. All right, temperature change. We had a formula for that. It was Q equals mass times the specific heat times the change in temperature. That formula should look really familiar to you if you were here the last couple days. All right, the mass of the water. This time, mass does refer to grams. So we want to put in the 325 grams, not the 18.06 moles. We changed it into moles because we're going to need that when we tackle the freezing part of this. But for temperature change, our formula has a lowercase m, which means mass in grams. Now the letter C. For the substance water, it's 4.18. Delta T, the temperature change. It's starting at a temperature of 45 degrees, and it's cooling off all the way down to 0 degrees. So the temperature change is negative 45 degrees. It's really important you put that negative in there. It's losing 45 degrees. It's not getting 45 degrees hotter. Multiply these together on a calculator. The result is negative 61,132 joules. Next, we're going to figure out how much heat is involved in the freezing process. And based upon the last couple of questions, we know that we're going to end up with kilojoules for that one. And I need to combine together my energy from these two processes. So I need them both to be in kilojoules. Let's make the change right now. This is negative 61.132 kilojoules. Now let's go down to freezing. Take the amount of water that we intend to freeze. Multiply by a fraction. Freezing is the delta H solidification value. Freezing means solidifying. We just used that value in the previous problem. It was negative 6.00 kilojoules for every 1 mole of water that we're going to freeze. It's a negative number because to freeze water, the water has to release heat energy. Releasing energy has a negative number for its delta H value. When you multiply these together, it's negative 108.4 kilojoules. There's just enough room left on the screen for the total. We need to add together this amount of heat and this amount of heat. The negative 61 kilojoules is the heat lost while the temperature is decreasing down to 0, and the negative 108 kilojoules is the heat lost in the process of turning the liquid into the solid water. If we add these together, we'll get the total heat loss during this entire process. The result is negative 169.5 kilojoules. Moving to the next question. How much heat energy is used to vaporize 3.5 moles of chloroethane at its normal boiling point, 12.3 degrees Celsius, given the delta H vaporization value for chloroethane? This time, We are given our quantity with moles. That saves us that entire step of having to turn grams into moles. So write down the given amount of the substance chloroethane. Multiply by the conversion factor. We are vaporizing it. So we want to know delta H vaporization, and that is the value given to us. 24.7 kilojoules for every 1 mole of the substance that we want to vaporize. Multiply these together on your calculator, and please write the answer down right in this position on your paper, and don't forget the label. If you want full credit on the assignment, I'm expecting that you yourself can multiply these together and get an answer there. All right, next question. How much heat is released when 0.667 moles of sodium hydroxide is dissolved in water? We're going to need the delta H solution value for this, and that's given in the problem. Again, it's convenient that this quantity has moles. That means we don't have to turn grams into moles. So write down the given amount. Multiply by the conversion factor. This question talks about dissolving the substance in water, so we want delta H solution, and that is that number given in the problem. This delta H value is negative. That means that heat is released when the sodium hydroxide is dissolved in water. Imagine you were doing this as a lab experiment. You're holding a test tube in your hand. You pour water in that test tube. It's going to feel a certain temperature to your hand when you're holding it. Now, when you drop in the sodium hydroxide particles into that water and they start to dissolve, that process is going to release heat. You would feel that because you're holding the test tube. If that process releases or produces heat, it's going to feel like it's getting hotter to you as you hold the test tube. Multiply together these two values, and please write the answer in that position on your paper. Again, don't forget the label. All right, moving ahead to our final question. Calculate the heat transfer that occurs in the following process. We begin with 500 grams of ice at the temperature -8 degrees Celsius. We apply heat until the ice melts, turning into liquid water. We keep applying heat. The temperature raises up, and when the water reaches 100 degrees Celsius, which is the boiling point, it is going to vaporize. We continue applying heat to the resulting steam, and eventually when we take the final temperature of the steam, we find out that it has raised all the way up to 126 degrees Celsius. What is the total heat transfer in this entire process? So this is going to take a lot of steps because temperatures are changing, and there's a formula that we use to do that. And there's also state changes that are happening, and we have a way to find the heat for that. So one thing I'm for sure going to do, and I'm going to have it be my step 1, is I'm going to turn the grams into the moles. Because I know that when I'm doing the phase change parts, I need to have moles, not grams. So 500 grams times, our substance is ice. Ice is like water, right? So it's the 18.0 grams per 1 mole. On a calculator, 500 divided by 18 will get you that result. That's how much ice we're talking about. All right, now step 2. This is where we're going to calculate the heat. But we're going to do it in a whole bunch of stages. First, we're raising the temperature. We're going to do a temperature change from -8 degrees up to 0 degrees on a thermometer. After that, the ice is going to melt. So we're going to do delta H fusion. Remember, delta H fusion meant delta H for the melting process. After the ice melts, a temperature change is going to happen. The temperature is changing from 0 degrees on the thermometer all the way up to 100 degrees on the thermometer. At that point, another phase change happens. The liquid water is going to vaporize and turn into gaseous water. The delta H value we're going to be interested for this is the vaporization value. Finally, even after it vaporized and had turned into steam, there's an additional temperature change that takes place. So we're going to do another delta T when the temperature goes from 100 degrees up to the final temperature of 126 degrees. Let's tackle all 5 of these stages, and then at the end we can add it all together to get the total. All right, heat transfer during temperature change uses this formula. The mass is 500 grams, not the 27.78 moles. The value of C is 4.18. And the temperature change when it goes from -8 up to 0 is 8 degrees. It's a positive 8 degrees. The temperature is rising. Multiply all 3 of these numbers together and write down the answer in that position. And that's going to be in joules. Now, 2 of the stages involved phase changes. And when we do the work for that, we're going to end up with kilojoules. So we want everything to be in kilojoules. So you need to take your answer you just got for joules, divide that by 1,000 to get the answer in kilojoules. Now let's do the second stage of the process. We want to do a calculation that involves delta H fusion. So write down the quantity of ice that we have. This time it's the number that uses moles, not the number that uses grams. And our fraction will have the delta H fusion value, and that's given in the story. We've used it earlier in this lesson already, 6.00 kilojoules for every 1 mole of ice that we intend to melt. Take your calculator and multiply these 2 together and write the answer down. This time it's kilojoules. The next stage of the process is back to a temperature change. So we write down our calorimetry formula. And make the substitutions. We have 500 grams of water. 4.18 is the specific heat of water. And the temperature is changing from 0 up to 100. So it increases by 100. Type this in to get the answer. It's going to be in joules. And don't forget to change that answer into a number that is in kilojoules. All right, now another phase change happens. The liquid water is going to turn into vapor. So let's do a calculation involving delta H vaporization. Write down the amount of the substance and multiply by the fraction. Delta H vaporization for water is given to us right at the end of the story problem. It's 40.7. multiply together the two numbers and write down the result right there in kilojoules. All right, our final stage, back to a temperature change. So we'll use the calorimetry formula. The mass of the water is 500 grams. The value of C is 4.18. And the temperature raises 26 degrees. Multiply these three numbers together, getting the answer in joules, and then change that to an answer in kilojoules. All right, the final thing to do is simply to get the total. What is the total energy transfer that takes place in this entire process? You're going to take this value, this value, this value, this value, and this value, so all of the ones with kilojoules, and add them together to get this total in kilojoules. Thank you for working on this assignment. Please make sure you turn your paper into the substitute teacher. It is not accepted late. I hope you have a wonderful spring break. See you in a week from now.